Hello everybody. I welcome you all to NCAS Geology class. Today I will discuss about the topic that is ore genesis. How ore minerals are being produced and how they are found to be distributed in different sectors of the earth. That I will discuss. We know that Earth's crust presents different sectors which are noted for the occurrence of different types of minerals or ore deposits. And these ore deposits are not uniformly distributed over the Earth's surface. There are certain sectors which are rich with respect to certain mineral deposits, and other sectors are there which are totally found to be barren. So there must be some factors, there must be some processes by virtue of which these ores might have been produced, and accordingly they have been concentrated. So that aspect will be discussed, and it can be said that the processes by which the ore minerals are produced, they constitute the processes of ore genesis of the minerals, and broadly they can be categorized into three types: igneous process of origin of ores, sedimentary process of origin of ores, and metamorphic process of origin of ores. So let us discuss the igneous process, which is the most primary source of formation of all metallic minerals or ore deposits. We know magma or lava, which is found to erupt into the crust or to the surface of the earth, they carry with them all the metallic components, and these components are found to be deposited through cooling consolidation of magma. And this cooling of magma involves several processes such as fractional crystallization, gravitative settling, filter pressing, gaseous transfer, liquid immiscibility. So these are the processes by which magma undergoes cooling, consolidation, and concentration of minerals and ores. And what are the different methods of ore concentration? The methods and the typical sites of igneous method of formation of minerals include the following. They are magmatic process, hydrothermal process, pegmatitic process, and volcanogenic massive sulfide deposit process. These are the four processes by which most of the metallic mineral deposits that we see to occur in different geological environments, they owe the origin to these four processes. And besides that, we have the porphyry deposits associated with the hydrothermal activity, this hydrothermal process. Reef deposits, they are also associated with hydrothermal process. Vein deposits, they are also hydrothermal in origin. But these are some of the specific deposits. Because of their very form, they provide porphyries or big grains. In the rift environments, generally we find the occurrence of ore deposits, and the highly valuable minerals whose concentration in magma is found to be very, very low, they occur as vein deposits, as we find in case of gold. Gold generally occurs in veins. We cannot get veins in thick masses. They occur mostly in form of veins. So, igneous process involves magmatic concentration, hydrothermal process, pegmatic process, and volcanogenic massive sulfide deposit process. These are the four major processes by which the ore deposits produced by magmatic process are found to originate. So let us discuss what is magmatic concentration. So magmatic concentration gives rise to syngenetic mineral deposits. And the processes are early magmatic process and late magmatic process. In early magmatic process, the ore deposits are either produced earlier to the formation of silicates, or they are found to be produced simultaneously with the formation of the silicate minerals. And the processes are magmatic dissemination, segregation and injection. By these processes, these ore minerals produced early are found to be concentrated within the rocks. And if we talk about the late magmatic process, it involves residual liquid segregation and injection and immiscible liquid segregation and injection, as a result of which the minerals like magnetite, chromite, ilmenite, pyrite, platinum group of elements, titanium vanadiferous magnetite deposits, Pb, zinc, copper deposits, nickel bearing chalcopyrites and diamond. So these are some of the important deposits which owe their origin to magmatic process. It may get concentrated in early magmatic stage or in late magmatic stage. And they are the direct product of cooling and consolidation of magma, and they give rise to syngenetic mineral deposits. The examples where we find such type of deposits, the common example is Panna diamond in case of MP, associated with kimberlites, and Sukinda chromite associated with ultrabasics, that is in Odisha. Platinum group of elements found in ultrabasic rocks, as we find in semi-pearl complex of Odisha. So ultrabasics, they concentrate PGE group of elements. Ultrabasics, they contain chromite, they contain magnetite, and kimberlites, they present diamond. Similarly, lead and zinc of Hesatu Belbathan belt of Bihar associated with granitic rocks. Nickel chalcopyrites of Singhbhum associated with granitic rocks. So these are the deposits essentially associated with the cooling of magma, either in early stage or in late stage of magmatic cooling. So let us discuss what is hydrothermal process. This process involves cooling and consolidation of minerals from hydrothermal solution, and it gives rise to epigenetic mineral deposits. So what is hydrothermal solution? Towards the last part of the magmatic cooling and consolidation, when almost all the silicates have crystallized out, the residual liquid is the hot fluid, which is found to be rich with volatiles, certain metals which have not been consumed, and with water. So this is called as hydrothermal fluid, temperature ranging from 550 to 50 degrees centigrade. And this hydrothermal fluid, while passing through the fractures, fissures or crystalline interstices, other structural weak planes found in the country rocks or found in the magmatic rocks which have produced this magmatic fluid. So in them, this fluid passes and under suitable conditions gives rise to epigenetic mineral deposits. The mineral deposition involves two processes. These are cavity filling process and replacement process. As the cavities are created within the magmatic mass which undergoes cooling and formation of rocks, in them the cavities may be produced which give rise to primary cavity, or because of forceful intrusion of magma, the magmatic mass may be fractured, fissured, jointed, faulted, and the overlying rocks may be affected by this intrusive activity of the magma, and those channels serve as the cavities, and these cavities are found to be filled up by the hydrothermal fluid through mineralization, through the reaction with the wall rock, and these are cavity filling types and replacement types. So, mostly sulfide deposits of different metals and silicates of economic value develop by above processes. The cavity filling deposits provide crustified vein, fissure veins, ladder veins, saddle leaves, stockworks, vesicular and pore space fillings. That means the cavities are there, and in the cavity the minerals are deposited, forming crustified vein and other vein types, fissure veins, ladder veins, these are stockworks. So these are the deposits which are found in the cavities. From these deposits are formed from the hydrothermal solution, direct precipitation from the hydrothermal fluid. And in case of replacement deposit, the reaction takes place between the invading hydrothermal solution and the wall rock through the openings, where the base metal sulfide deposits are found to be deposited through replacement, which is found to be followed by concomitant precipitation of mineral matter from the hydrothermal fluid, so that the structure of the mineral replaced is found to be preserved, because of which we find the formation of pseudomorphs of replaced minerals after the replaced minerals. Pseudomorphs of the minerals which are replaced. So, let us say if we have any mineral which is occurring there in the country rock and that has been replaced, let us say the mineral is having a cubic shape. This mineral is removed and another, let us say, zinc sulfide deposit is taking place in this place, and this zinc sulfide will take the shape of the cube, which was the original shape of the mineral which was occupying that place previous to the replacement. That's why the replacement deposits are these deposits of the minerals which take the shape of the replaced minerals, and this process develops through molecule per molecule replacement. Molecule per molecule replacement. One molecule is replaced and simultaneously there is deposition of the mineral matter in that place, so that the internal structure of the replaced minerals is preserved by the replacing minerals. So, replacing minerals take the morphology of the replaced minerals. So, replacing minerals form the pseudomorphs after the replaced minerals. So, this type of formation takes place, and The cavity filling and replacement, these are the two processes by which hydrothermal mineral deposits originate, and commonly these give rise to the sulfides, lead zinc sulfide of Rajasthan. So the deposits are found to be epigenetic in nature because they occupy the cracks, fissures which have developed in the rock that has already formed. Before the formation of these deposits in them, they have existed. That's why these deposits are said to be epigenetic, because they are found in the rock after they are found to develop in the rock after the formation of the rock which contains them. So let us switch over to the next part of this igneous origin of the ore deposit, that is pegmatic process. Pegmatites. If we take into account the various stages of magmatic cooling and consolidation, the stages are orthomagmatic stage, which is high temperature part of the magmatic cooling, pegmatitic stage or pneumatolytic stage above 575 degrees centigrade, pyrometasomatic stage between 500 to 800 degrees centigrade, and hydrothermal stage. This gives rise to hydrothermal deposit. This gives rise to magmatic concentration deposit, and we have in pegmatitic stage, the volatiles are found to dominate. Pegmatitic stage forms the intermediate stage in magmatic cooling, and in this stage the volatile is dominant, as a result of which large grains are produced. The texture becomes paneomorphic. Many rare minerals and metals are found to be produced in this stage, particularly in intermediate stage of magmatic cooling and consolidation, particularly in intermediate magmas or in granitic magmas. The minerals are beryl, apatite, lepidolite, spodumene, cassiterite, wulfenite, molybdenite, silicite, tourmaline, topaz, uranite, columbite, arsenic, silver, beryllium, tantalum, niobium, and rare earth elements. So these are some of the major minerals, elements that are found to develop in the hydrothermal stage of magmatic cooling and consolidation. Example, the pegmatites of the Esternhardt group of rocks. They contain these rare minerals: apatite, beryl, lepidolite, spodumene, then cassiterite, tourmaline, topaz. These are the minerals, valuable minerals that are found to develop in the pegmatitic stage of magmatic cooling and consolidation, and they give rise to syngenetic mineral deposits. They give rise to syngenetic deposits because they are associated with the same magma which produced them. They are associated with the same rock that produced them. That's why they are syngenetic. Besides these, we have another important method of origin of the ore minerals, that is volcanogenic massive sulfide deposit process, VMS process. This deposit represents the ancient buried products of vents associated with the ocean floor volcanism along mid-ocean ridges, back arc basins, and islanders, because these are the sites where magma is found to be erupted and the superficial features are found to develop in form of mid-ocean ridge, in form of island arcs. So these are the sites where there is occurrence of the volcanogenic massive sulfide deposits. and they are associated with black smokers and white smokers. So, what are the processes that are involved in volcanogenic massive sulfide deposit? The seawater penetration. First step is the seawater penetration. Cold seawater percolates down through the fractured basaltic crust, and this basaltic crust is developed because of basaltic magma intrusion. So, along those cracks the water enters and it reaches the magmatic chamber. Because the magma undergoing cooling superficially develops the solid crust, which is basaltic crust, and below it the magma is still found to be in liquid state, and those through the fractures the water goes inside and meets the magmatic masses that lies below the solidified basaltic crust. So this percolating cold seawater reaches the magma chamber through the cracks, fissures, and mixes with the magmatic fluid, and the temperature of the fluid so produced is found to be lower, and it ranges between 350 to 400 degrees centigrade. At this temperature range, this magma becomes enriched with volatiles with leached components of metals. Metals are leached from the basaltic rocks, and in this condition this hot fluid enriched with metals tries to erupt through the vents, and it erupts into the sea floor as smokers, and in the sea floor it comes in contact with the cold seawater, temperature drops, and the magmatic fluid undergoes cooling and precipitation of metallic sulfides. And these metallic sulfides, they form the chimneys, chimney-like deposits. Continuous release of this hydrothermal fluid through fissures, vents leads to massive deposition of sulfide metals, which give rise to mounds of stratified sulfide deposits. Thus, it can be said that VMS deposits are the products of two smokers, that is black smoker and white smoker, and these two smokers vary from each other with respect to their composition and temperature. The black smokers are rich with Pb, iron, zinc, copper, whereas the white smokers are rich with silica, barium, calcium, because of which the color becomes white. So, the compositionally black smokers and white smokers, they vary, and black smokers is bit at a high temperature and white smokers are found to be at a lower temperature. And these smokers, these smokers are nothing but these are the vents through which the compositional different materials derived from the basaltic magma is found to erupt into the sea floor, and because of their very composition they give rise to sulfide deposits. So let us know a little about these smokers. Smokers are black smokers and white smokers, and black smokers really give rise to the sulfide deposits, and it is overlain by the white deposits made by the white smokers. So black smokers, it is the main builder of the VMS deposit. It represents the vent through which hydrothermal fluid at a temperature range 350 to 400 centigrade rich in black colored matter such as iron, copper, zinc, H2S, which is erupted into the ocean floor, where it comes in contact with the cold oceanic water, as a result of which different types of minerals such as chalcopyrite, pyrite, sphalerite are precipitated. These precipitated minerals form chimney-like structure with phase by phase formation of such sulfide minerals one above the other, mound like massive sulfide deposits are developed and which get buried and preserved as massive sulfide deposits. That is VMS. So, black smokers can be called as the modern analog of ancient volcanogenic massive sulfide deposits or sulfide ore formations. In case of white smokers represent white color, and these smokers, they are found to be more evolved and they occur towards the peripheral part of the same hydrothermal system that yielded the black smokers. If the black smokers the main chamber, it becomes the sideways peripheral zone. White smoker, black smoker. So it occurs at a lower temperature, it occurs at a higher temperature. It is represented by the white minerals, it is represented by the dark colored minerals. So white smokers, they have a temperature range of around 200 to 300 centigrade. The components present are the barium, calcium, silicon. These are the major constituents, and they are very low in sulfide content. Hence, they give rise to white smokers, or white particles are found to be precipitated out of the emanations of this fluid through the vents. This fluid on eruption to the sea floor gets cooled on mixing with the cold sea water and gives rise to chimneys of mineral deposits such as barite, anhydrite, silica or chert. So these deposits lie over the VMS deposit, and therefore white smoker mineral deposits serve as the pathfinder to the VMS deposit. That has been displayed in this chart. Magma forms the basaltic crust, develops the cracks into this seawater comes and mixes with the minerals with the magma and leaches the minerals from this basaltic crust, and the fluid becomes rich with metals. And with volatiles, it is found to be erupted as black smokers because of their very color, because they are found to be rich with iron, copper, zinc. So black color, so that's why it gives rise to black colored fluid, which is found to be erupted into the sea floor at this temperature range and gives rise to deposit, and sideways from the peripheral part of this fluid emanation rich with barite, anhydrite, silica that erupts at a lower temperature. It provides white smokers. So white smokers, they serve as the pathway to find out the massive sulfide deposit at a little greater depth compared to the white smokers. And if we take into account the VMS deposit, the VMS are found to be present worldwide in the ocean floors, and they are divided into three types based upon their association either with the island arcs or with the mid-oceanic ridges. They are divided into Cyprus type, Basit type and Kuroko type. Cyprus type, it is associated with the mid-oceanic ridges, and here the black smokers are found to be erupted. They are found to be associated with the basic volcanic, that is ophiolites, and it gives rise to rich copper deposit, cupriferous pyrite, zinc, nickel, chromium, manganese, silver, gold deposits, and their first study took place in the Mediterranean Sea in Cyprus, and they are associated with trudosophiolite, the copper associated with trudosophiolite that has been studied in Cyprus. That's why this type of copper deposit which are produced from this volcanizing massive sulfide process is called as the Cyprus type, associated with mid-ocean ridges and intimately linked to ophiolites. Besides this Cyprus type, we have another two types which are associated with the associated with the island arcs. In the early stage of the island arc formation, the magmas are found to be alkaline, and in this stage, which is the juvenile or nascent arc stage, in the back arc basin or in rift and marginal basin, the smokers, black and white, they are found to undergo cooling and deposition. Sulfide deposits are produced, copper sulfide, iron sulfide, minor amount of zinc and PB sulfide, they are found to be deposited. Along with the Greywacke succession at the vents giving rise to this type of deposit is found to be of diffuse type, because the fractured Greywacke succession through which the enriched magmatic fluid passes and is found to be erupted into the ocean basins, and there they give rise to these sulfide deposits. Zinc, Pb, copper sulfide deposits are produced, and the name has been derived from its study from basic copper mines Shikoku, Japan. So, the basic type that are associated with the intermediate stage of development of island arcs, they are linked with Greywacke succession. The deposits are copper sulfide, zinc sulfide, iron sulfide, and it can be said that they are mostly from black smokers. And in Kuroko type, it is associated with the matured stage of evolution of the island arcs. Here, the associated magma is felsic type, felsic volcanics, dacitic or rhyolitic, and they represent polymetallic sulfide deposits arranged in a vertical zone, with base represented by the black smokers and top represented by the white smokers. And their study were made in Japan Sea, from which the name has been derived. The polymetallic sulfide deposits which are found to be produced in the matured stage of the island arcs are the black core at the base, which is called as Kuroko. That means Kuro means black, Ko means ore. Black ores are found to be at the bottom, related to the emissions through black smokers. It is followed by yellow ore, Oko, which contains chalcopyrite and pyrite and rich in copper. It is followed by the siliceous ore and the barite cap, which form the upper zone, and they form Sirocco deposit. That is, Sirocco means white ores. Siro means white, Co means ore. The white ores towards the top. So it takes place at a lower temperature from white smokers, and this takes place from black smokers. So this is polymetallic deposit that is associated with the Kuroko type of the volcanogenic massive sulfide deposits, and they are studied in Okinawa Trough of Japan, that is Akita Hokuroku district of Japan, where this deposit is being found. So these are the three major environments in which the volcanogenic massive sulfide deposits are found. And besides this, we have the other method of mineral formation associated with the igneous activity, that is porphyry deposit. Porphyritic minerals, porphyritic rocks are produced because of their condition of cooling, because of the presence of the components in the magma. The porphyritic rocks are being produced. So porphyritic deposits are associated with the porphyritic rocks. What are the porphyritic rocks? The porphyritic rocks are the diorites, quartz monzonites and granodiorites. And these porphyritic rocks, they show bigger grains surrounded by smaller grains. Bigger grains might have been favored by the high molecular concentration of those components in the magma, followed by the other components which are having less concentration. And these porphyritic rocks, or the dioritic and monzonitic, granodioritic rocks, which are intermediate igneous rocks or acid igneous rocks, in them the porphyritic minerals are found to develop, particularly along the convergent plate boundary zones, and in island arc environments, continental and island arc environments. The metallic sulfide deposits occur as disseminated bodies or as stockworks in porphyritic intrusive igneous rocks and the surrounding country rocks. So porphyritic igneous rocks, they contain some of the typical minerals as are found in case of the magmatic deposits that are associated with the pegmatitic process. In case of pegmatites, the minerals which are produced, they are associated with the volatiles. The grains produced are very bigger in size, and similarly in case of porphyritic deposit, the magmas are acidic or intermediate in composition, and in this magma some of the economic minerals are found to be concentrated along the convergent boundary zones in the island arc environments, and these deposits generally form at a depth of around 1 km 6 kilometers within the arcs, and they are represented by chalcopyrite, chalcocite, bornite. These are sulfide deposits, sphalerite, cinnabar, energite, spodumene. These are the galena sulfides. They are associated with and the associated gangue minerals are quartz, feldspar, and biotite, because the rocks are acidic igneous also. They are represented by quartz and feldspars. So these mineral sulfides they are found to develop in the island arc environment in the convergent boundary zones, and the process of origin of these porphyry type of mineral deposits involve the following: that is, subduction of the oceanic plate below the continental plate. Partial melting of the oceanic plate produces intermediate magma because of mixing of trench sediments with the crustal and the crustal rocks with the basaltic magma, as a result of which the magma becomes alkaline or acidic to intermediate in composition. This magma upwells in faces crystallization, it releases hydrothermal fluid which is charged with volatiles such as sulfur, chlorine and water. This hydrothermal fluid fractures the consolidating intermediate and acid igneous rocks, escape through them into the country rocks, and they release their metal content as sulfide deposits which occupy the cracks and cavities through cavity filling process and replacement process. So, this process of origin is a type of hydrothermal mineral deposit. And here it is seen that the cracks along which the hydrothermal fluid passes, it develops a alteration zone, central alteration zone, and gradually the sides are found to be precipitated with mineral matter, and the central zone is called as the core zone, which is a potassic zone. It is zone of alteration. Zone of alteration develops due to the passage of the hydrothermal fluid through the cracks. So in the central portion, the core portion, it is potassic zone, followed sideways by phyllic zone. The core zone is the real zone where the sulfide deposits are found. With the K-feldspar muscovite, the sulfides are copper sulfides, molybdenum deposits. These are found to be in the central zone, and away from the center we have the phyllic zone. It is represented by quartz sericitic minerals and pyrite, and the mineralization is of moderate mineralization. Still away from the phyllic zone outwards, the argillic zone, or it is the zone of weak mineralization, developed in the clay mineral zones, or clay minerals are found to develop. And still out the propylitic zone, which is chloritic zone or epidot calcite zone, and very low grade ores are found to be there. So, in case of this porphyry deposit, the hydrothermal fluid produced in the convergent boundary zones, they give rise to the economic mineral deposits. They develop the alteration zone with core portions represented by copper, molybdenum, and surrounding rocks surrounding the core. The phyllic zone, argillic zone represented by clay minerals, and propylitic zone represented by the chlorides with very low grades, and rich grades are found to be in the core zone. And the example is Bingham copper deposit, which is the world's largest copper deposit, and Malajkhand copper deposit in Madhya Pradesh, which is the largest copper deposit of India. And beside this, we have the alpine Himalayan zone, where most of the copper deposits are found in all the Himalayan districts: Uttarakhand, Jammu Kashmir, Sikkim, Arunachal Pradesh, Himachal Pradesh. So, these are the districts where these sulfide deposits are found, porphyry coppers are found, and world's 60% copper comes from this environment, which are produced from hydrothermal fluid that results due to formation of the intermediate magma that provides the hydrothermal fluid that enters into this environment of the subduction zones where island are produced, and in these island environments these mineral deposits are commonly associated, and generally deposits are found in the alteration zone as shown here: core zone, phyllic zone, argillic zone, tophylitic zone. So, world's largest copper is derived by this process, is produced by this process. Then the reef deposits are associated with rifting of the continents, continental rifting or oceanic rifting. Oceanic plates are stretched, continental plates are stretched, extension takes place, thinning takes place, and finally fracturing or rifting of the plate, through which basaltic and rhyolitic magma erupts, and it gives rise to the economic mineral deposit through hydrothermal process. The examples are, and here the lavas which erupt, they generally provide the vesicles, and vesicles become the site for the precipitation of copper, iron, zinc, Pb, nickel, Pg group of elements, then uranium. So the vesicles, they are the site for accumulation of these minerals or metals, and from these vesicles they are derived and transported to the surrounding environment where they give rise to economic concentration of these metals, as we find in Quincy, Michigan iron copper nickel deposit of USA. Similarly, we have Pennsylvania iron ore deposit USA, Sukinda chromite deposit Odisha, Singhbhum copper deposit Bihar. So the process involves rifting. Rift zone is accompanied by extrusion of basaltic and rhyolitic lavas. And these lavas, they yield the hydrothermal fluid, and that hydrothermal fluid gives rise to these deposits. Besides this, we have the veins. Veins generally concentrate the highly valuable metals that are low in their concentration in magmas. The hydrothermal fluids derived from the granitic intrusives along the convergent plate boundaries and interplate setting try to escape through the extension of fracture zones, faults, and during their process of extrusion, the metals are found to be precipitated along the fractures as mineral veins or mineral lodes. The deposits form epigenetic deposits. So fractures are found to be filled up by the mineral metal from hydrothermal fluid. Various types of metal-rich vein deposits include gold, silver, copper, and the metal sulfides occur with other gangue minerals such as quartz and calcite. Example of California gold deposit in Sierra Nevada region, Klondike gold deposit of Canada, Kolar gold deposit of Karnataka, Singhbhum copper deposit in chalcopyritic veins in shear zones. So this is all about the igneous origin of the minerals or metals. So the main process are magmatic process, hydrothermal process, and the volcanogenic massive sulfide deposit process or porphyritic deposit, porphyritic mineral deposit process. These are the main processes by which the minerals are found to develop in igneous environment, and all the igneous minerals or igneous rocks are the primary source. They serve as the primary source of all metallic deposits that are found in different sectors of the earth, particularly the sectors where the magmas are found to erupt. These are the convergent boundary zones and these are the divergent boundary zones, or in the intraplate setting or along the centers where hot mantle plumes are found to be erupted. So, volcanogenic massive sulfide deposit, pegmatitic process, then magmatic process and hydrothermal process. These are the main processes by which the ore deposits by igneous process are produced. This is all about the igneous origin of the ore deposits. In my next talk, I will discuss about the sedimentary origin of the ore deposits. Thank you all for your patient hearing to my this talk. Thank you.